What are three things the audience is going to learn today from your presentation?
Well, what we're going to learn about today is a category of applications that have been, I would say, largely pretty rare for most software developers, which is real-time applications. So we're going to kind of learn a bit about what those are. We're going to learn about what sorts of businesses tend to have them, and also how to actually go about implementing them using Akka.net and the actor model. So that's what we're going to cover today.
All right, Aaron. So it's a pleasure to have you here, and the virtual stage is yours.
All right. Thank you very much. So let's see. I'll just go ahead and dive right into my presentation here. So my name is Aaron Stannard. I'm one of the creators of Akka.net, and I've been working full-time on building Akka.net applications with our customers and also here in-house at Petabridge for about 8 years now. And today is my talk called Death to Latency, which is kind of distilling a lot of what we've learned over nearly a decade of this work. Actually, exactly a decade of this work, because I was doing this at a company prior to Petabridge for 2 years too. And this is all about how to build non-trivial, non-traditional, business-critical applications. Enter the real-time web. So when we talk about the real-time web, what do we mean? These are internet applications with soft real-time processing guarantees, not to be confused with hard real-time guarantees. So here's a critical difference or distinction between these two types of software. Hard real-time systems tend to be embedded software. These are things like the electronic brake control system on your car or the fly-by-wire system for a fighter jet, that type of thing. Those systems tend to be built for embedded operating systems like VxWorks, and using, let's say, more bare bones sort of programming constructs like .NET Micro Framework or C++. And those have constraints where, let's say, if this block of code doesn't execute in 50 milliseconds, the operating system seg faults. That's what a hard real-time software system is. And unless you're building embedded systems, you're probably not interested in that. What we're talking about are soft real-time systems, where the basic principle is that the longer it takes to do something, the less useful it is. So the reason why this is such is because data tends to become stale quite quickly in these systems. For example, if we're building a real-time chat system and it takes 10 seconds for you to see my reply to your message, that is not going to be a very useful or good user experience. And users will switch to some other alternative if those guarantees can't be met by the software. Now, chat's one example of that, but you can also look at others like video games or, let's say, real-time e-commerce applications such as auctions, or maybe participating in volatile markets such as cryptocurrency or sports betting or stock trading, that type of thing. The other sort of issue that can emerge from real-time applications is that you actually can create business risk or potentially safety hazards if you don't meet these real-time processing guarantees. So a good example for that shows up pretty frequently in the Akka.net space is industrial Internet of Things. We have a lot of customers who use Akka.net to help automate let's say manufacturing systems, for instance. And some of these machines are operating saws or laser cutters. And in some cases, maybe they're operating things like compactors or spindles, which can be moving quite fast or operating with very large amounts of horsepower. And so if you need to send a signal to shut a device down because it's operating outside of its safety parameters, if you can't guarantee that between detecting that the machine's not operating safely and shutting it down if that can't be executed in a short period of time, your software is actually dangerous. So this is all about this talk, how to build these types of real-time applications. Now, not to go ahead and let's say beat a dead horse here, but just to drill in one more time, what's real-time versus not, let's go ahead and compare two applications that are in pretty much identical domains where one has a real-time requirement and one doesn't. Voice chat. If I go ahead and make a VoIP phone call to my wife, I need to be able to chat with her in real time. The real-time interactivity is what makes that application useful. If I just needed to send a message to my wife, asking her to pick up, coffee while she's at the grocery store, or maybe she needs to send me one asking me to go ahead and take care of something on my way back home. She can just leave me a voicemail and vice versa, where I can go ahead and check that asynchronously. This doesn't have a real-time processing requirement in the same way that this does. And this shows up in a bunch of other business domains as well. There are lots of businesses that have real-time domains. In fact, many more than there used to be. And this is driven in part by improvements in technology. A good example, WebSockets being available in most major web browsers now allows you to build lots of client-side applications that can support real-time interactivity. Whereas in the era before WebSockets, this was much more difficult to facilitate than it was before. On top of that, bandwidth speeds are generally increasing around the world, and it's also a lot cheaper to connect devices to the internet than it was before. So these are some examples of domains that all come with some type of real-time processing requirement. Sports betting, dynamic pricing, clickstream analytics, multiplayer video games are another classic example of this. And there's going to be many more domains like this that emerge over time. If you're working for a traditional business, most of your real-time processing will show up in areas such as fraud monitoring, trying to go ahead and process online transactions, or maybe doing things like search or collaboration. These are all different sort of, let's say, kind of more business-centric areas where a real-time requirement might appear inside your company. So in order to build real-time software, what distinguishes this from, let's say, a traditional CRUD application or most stateless web applications? Well, there's three business questions we have to be able to answer in order to build an effective, reliable, real-time software application. The first question we have to be able to answer is, for a single instance of some critical business operation, how do I guarantee that I can bound the latency under n milliseconds, where n is a value that is specific to your requirements? So for instance, we have some customers that use Akka.net for doing foreign currency exchange trading. They tend to work for either investment firms or big banks in Europe for the most part. And so they have requirements that look like, okay, I need to be able to guarantee that within 5 milliseconds of detecting this change in demand for this currency pair, I need to be able to open a new order or close an existing position. How can I guarantee that I can, let's say, open and close those positions and detect the original market signal all under 5 milliseconds? Okay, so how do I do that for one instance, for one possible trade on one currency pair? Next is, okay, but if I'm a bank and I'm doing foreign currency exchange, it's very unlikely I'm going to have only one currency pair I'm interested in trading in. And it's also very unlikely that I'm only going to have one open trading position, meaning one, let's say, essentially one, let's say, order that's standing in an order book somewhere in a market. I'm probably going to have hundreds of orders at any given time. So how do I make sure I can guarantee maintain that real-time processing guarantee? So n milliseconds. So let's say n is 5 in this case. So I've got to be able to react to market information within 5 milliseconds for one trade. How can I make sure I can do that for 500 trades all in one process? So this is where we start getting into basic questions of concurrency and scalability here. And then finally, question 3 is, okay, I've been able to go ahead and guarantee that I can accomplish 500 different positions within a single process. But if that process becomes unavailable, I'm screwed. How do I make sure I can make this production worthy, where I have redundancy, fault tolerance, and the ability to transfer responsibility from one instance of my process to another in a manner that is safe? How can I do that and still maintain that real-time processing guarantee? And this is where we're going to start getting into some of the fun distributed programming concepts with Akka.net, such as Akka.cluster and Akka.cluster sharding. That's how we essentially implement this in the real world. So these are the three key business questions you have to be able to answer. And the most crucial one is question 1, obviously. This is a matter of changing paradigms around how we think about programming. Old paradigms will not work. And the oldest paradigm for building web applications is going to be let the database handle it. To which I normally react when I hear this come up from a customer or one of my own team members or from an open source user. No, your application will, this isn't a probabilities thing. This is a certainty. Your application will absolutely fail to meet any sort of demand once it gets beyond a non-trivial size if you're basically centralizing your source of truth inside a database. To give you an example of this, let's suppose we're building a real-time application that does clickstream analytics. So in this scenario, a user generates an event by clicking somewhere on a website, and I need to do something if this user produces these 4 critical events I'm looking for. That thing might be personalizing an offer for them to buy something. It might be sending them an email notification. It might be sending a push notification to their phone. It really depends on what your use case is. But the key factor here is that within a very short window of time of this user accomplishing these 4 events, I need to be able to send a message back to the user. If I don't send this message in real time, my quality of service decreases and the value of what I do for the user is going to fall. So I need to be able to observe this guarantee. And if I haven't seen all 4 of those events, I need to go ahead and continue to wait for them. So this is like a little state machine is the way to think about this. If we're going to centralize all of our state around whether or not a user has met those 4 events inside a database, this is probably the solution that you would use. It's called a read after write strategy, which is where I have my user operating a web client. So that's going to typically be a browser of some kind. I have my load balancer, all my stateless web applications, and then my database. And for argument's sake, our database could be something that is fairly consistent like SQL Server. So a user clicks around the website and manages to produce these 4 events. And I'm going to go ahead and see that event 0 arrives, and I'm going to insert event 0 into the database. And then I'm going to read back all the events for that user and see if the 4 events that I'm looking for have appeared or not. And I'm going to repeat this for all events until eventually the results I get back show that all 4 of the user's events have appeared, at which point I'm going to react and send that user a notification as quickly as I can. I actually tried building the first version of the app that inspired Akka.net this exact way. And the rate at which we were able to trigger this notification successfully and on time was beneath 0.1%. So effectively, this never worked. And the reason why this doesn't work is twofold. The first issue is that events don't arrive neatly in order like this in real life. They tend to arrive out of order or concurrently in this case, where events 0 and 3 might both arrive at the exact same time. And so when I read my results set back, there's no guarantee necessarily that all these clients are going to have a fully consistent view of what the other clients are doing, because all of these write and read operations are happening independently from each other. So there's no way to order things causally for a given user inside the system. So chaos ensues, and by and large, you're going to end up probably not achieving your goals back from this. On top of that, by the way, I should point out, as kind of one of the things I'm teeing up here, Akka.net makes this particular problem very trivial to solve. The other problem with this design, let's go ahead and set aside the concurrency issue, which is somewhat more sophisticated. The basic issue is that the overhead of this HTTP request coming in, this server making one database write and one database read, is going to set the minimum floor for your latency pretty high because of the amount of I/O serialization and even possibly things like disk I/O on the database server quite high. You're going to have essentially a higher starting latency than you would with the alternative design that Akka.net makes possible, which is called stateful programming. So old paradigms like centralizing our state in the database fail for a number of reasons. And when I say fail, I mean they fail to help us build real-time software applications. They fail because the I/O overhead is excessively high. On top of that, there's no application layer concurrency control, meaning that I don't have the ability to order all the different writes and reads for the same entity across all those clients. Everything is kind of a free-for-all, and there's no guarantee that I'm going to get the results that I'm expecting back, even though all 4 events were produced by the user. That's actually a fairly common problem, particularly if these events are happening pretty rapidly. The last big problem that these old paradigms have is centralization. The database becomes an inescapable single point of bottleneck inside these software systems. And as a result of that, once your system exceeds whatever capacity the database can handle, you're forced to start doing things like introducing downtime and vertically scaling. Or you're forced to try to introduce paradigms such as federation and partitioning inside your database as well, which is going to make your infrastructure more complex, and it's also probably not going to help at all dealing with the original excessively high I/O and all the other problems that this introduces. I'm going to go ahead, since this is an hour-long presentation, I'm fitting into 45 minutes, so I'm going to go ahead and move past this part. So rather than talking about why old paradigms fail, let's talk about what paradigms can help us successfully build real-time applications. And in this case, the paradigms we want to look at are stateful application programming paradigms. So the principle that we're operating around is what's known as state locality, which is the idea that in order to produce the lowest possible, the correct result with the lowest possible latency, we need to remove unnecessary I/O from our system. And we need to operate, generally speaking, at a higher level of I/O. So given these two architectures, a stateless, let's say CRUD architecture, pretty similar to what we were just looking at a minute ago, versus a stateful architecture where the code that does the work is adjacent in memory to the information it needs to do it. Which of these two architectures will have a lower latency? Naturally, the stateful application architecture is going to be several orders of magnitude faster than its stateless counterpart. And the reason for that is really simple. The state locality, meaning that the data is adjacent to the work in memory, allows us to co-locate state and work together inside a single process, which eliminates a lot of I/O and pretty much all serialization. It also eliminates really expensive forms of I/O, such as disk and network. This also gives us a way of kind of reversing our architecture a little bit, where rather than polling a database for state changes, we have the ability to observe state changes happening in data structures we control as software developers. Therefore, it's possible for us to build a reactive model to state changes in the first place, where rather than polling the database and trying to guess if all the events we have are there, we can see those 4 events from my previous example. We can see the 4th event arriving the second it's available, or really more accurately, the microsecond it's available, and we can react immediately. So this allows us to go ahead and strip out several different sources of latency all at once. And then on top of that, the other thing state locality allows us to do is we can have multiple correlated domain objects. Let's say I have, in addition to, if I go back to my foreign currency trading example, I have the state of the price, meaning this is sort of what the price looks like. I have the state of the order book. This tells me how many buy and sell orders there are, what prices they're available at. And then I have the state of my bank's trading position, meaning here's the amount of currency we bought at this price, and here's the target price we want to sell at. I can go ahead and have all 3 of those different in-memory objects correlate and react to each other to produce the lowest latency possible workload for my system. And that's what's going to allow us to successfully execute trades with lower risk inside this system. So this is the first big paradigm shift for meeting that first real-time processing guarantee, is we have to move away from these old paradigms of slamming everything into the database to actually treating our application itself as the source of truth for our software. So what this looks like is, let's say these are all different Akka.NET processes in this case. We have state that is resident inside one of these processes, and that's going to be the source of truth for our application. There's still a role for a database to play, inside these software applications, we can't get rid of the database entirely because it still performs useful functions for us. Namely, the database gives us a means of rehydrating state in the event that we need to roll out a new version of our software, in the event that an instance of our software fails, or in the event that we need to redistribute state in the future, maybe because we're scaling up in order to meet demand, or because there's some other type of as a new node joining the cluster with an updated version of the software, and we need to give that node some work to do so we're not wasting the hardware that it has available. So the first real paradigm for being able to guarantee that our work can be completed in under n milliseconds is to use a stateful programming model. So this means putting the state of our application in the driver's seat and treating the database just like cold storage in that case. So that's the first bit. Now, I haven't really given us a concrete example of how to do this yet. And I'm going to do that once we introduce guarantee number 2. How can I make sure that we can have n number of parallel instances of our operation all successfully complete under our real-time deadline? And this is where we enter the actor model. So this is Fabio. I abuse his likeness in many of our presentations. The actor model is a stateful programming model that makes it very easy to reason about distributing state for many different business entities in a low latency, easy to program fashion. This is what an actor looks like in Akka.NET. Now, this is a very simple, bare bones actor. An actor is basically a little self-contained microprocess that is going to process one message at a time. So the way we interact with our stateful objects is by message passing. And its state is just its internal fields and its internal properties. That's all that it is. There's no special type of object or interface you have to inherit from in order to create state in Akka.NET. This little logger here is an example of, let's say, a piece of state that belongs to this actor. I could also go ahead and have an in-memory dictionary or a custom record in C# or F# that I developed, whatever I want. And so this actor is going to have some strongly typed handlers that express what types of messages am I capable of processing. So in this case, I have a ping message. Every time I receive this ping message, I'm going to run this function right here, which is going to cause me to log the message I received. I'm going to generate a random interval that I'm going to use to reply back. And I'm going to use the scheduler to send a delayed response back to the sender. If I wanted to just reply back to the sender immediately, I could just take this sender property right here, and I could call sender.tell and send my response that way. That would be the lowest latency way of being able to produce a response in Akka.NET. But for this particular example, I use the scheduler, and that's just kind of for arbitrary reasons in this case. So how do you actually create an actor in Akka.NET? Well, first, you need an actor system. This actor system creates the address space that all the actors can use to talk to each other in memory. And when we enable things like Akka.cluster or Akka.remote, the actor system is also the unit of reference we use for being able to exchange messages over the network as well. Next, I need to create props. This is essentially the recipe for how to start a specific type of actor. So this is going to include a little new expression that specifies what actor type we're going to use and what constructor arguments we're going to use to instantiate this actor. I can then pass that props formula into the actor system.actorOf method. I can optionally give this actor a name if I want to. If I don't specify a name, a unique one will be chosen randomly for me. And then I get what's called an actor reference back to this actor. This actor reference is location transparent, which means that I can include this actor reference in a message, send it over the network to another actor running on another process, and that actor can reply back to this iActorRef, and the message will be magically sent back over the network to the original actor who sent it, even though they live in two different processes. So this is basically meant to be a handle for being able to reply back to an actor, and it's guaranteed to work throughout the entire Akka.NET network. And then finally, I can go ahead and use this actor reference to send a message using this little tell method right here. This is basically a little fire and forget API for being able to deliver a message to an actor of type ping actor. And this is one specific instance of it. I can have millions of actors running inside the same process. And that's like actually pretty common in Akka.net. And that's one of the ways we're going to achieve this parallelism that we're talking about. The way to think about actors and what they mean is that actors are essentially stateful cloud objects. So this actor has some state, and when a new event arrives, this is going to cause this actor's state to mutate potentially. Once this actor has observed its state transitioning from, let's say, its initial state to some target state, where this might be, we receive all the events that we need in order to fire this notification to a user, the actor can react in real time simply by invoking a web API, maybe sending a message to another actor, or maybe doing something slightly more interesting, such as writing a message to a WebSocket that gets rendered on a user screen. You can think of actors as sort of a way of wrapping a business entity inside your system. So users tend to map actors one-to-one to their business entities. So if I'm building, a real-time chat application, I might have one actor that represents my chat room, one actor for each of the different users that are currently participating in it, and actors that are, let's say, receiving messages from users are going to be pushing those messages into the chat room. The chat room will go ahead and update its record indicating what the most recent, let's say, buffer of chat messages looks like, and that'll get flushed over the WebSockets for all those users. Every single actor has a globally unique address. So there's some unique way of identifying it over the network. You can program against those addresses directly, but most people use those iActor refs that we talked about to message those actors. Actors accumulate memory. Actors accumulate their state in memory. So as messages are being sent to this actor, the actor is going to update its state and react accordingly. This is going to help us greatly reduce the amount of latency it takes to perform work inside our software. And then on top of that, actors have the ability to react to these state changes in real time without any dependencies on databases or cloud products or any other external infrastructure. You can, of course, use modules like Akka Persistence to make it very easy for actors to journal their state using event sourcing to a database like SQL Server or Azure Table Storage or Redis or MongoDB. And that's something that we use quite frequently in production applications. But that's something optional that you can opt into. It's not a requirement to have to use any of that. And actors tend to be, as I mentioned earlier, very inexpensive resources. It's very common to have millions of actors inside a single process if you're running a really large application. I have some customers that run as few as a couple dozen actors inside their processes, or some that maybe even only use 4 or 5 actors. The way to think about the actor model is that every single instance of an actor represents one instance of some key business entity inside your system. So if we're building, let's say, an IoT application, and I have thousands of different, let's say, temperature and volume sensors. Let's say I'm building something like a safety monitoring system for an oil pipeline, which actually is a real example of Akka.net being used in the real world. So I might have this big volume of events coming from all these sensors that are built on, let's say, hundreds of miles of pipeline. Well, I might have volumetric sensors, which measure changes in volume. And then I might also have temperature sensors, which measure changes in temperature as it so goes. And they have different safety thresholds depending on what type of sensor they are. Well, I can go ahead and have a root actor. Let's say my device of type A actor. This represents all volume sensors. Every single message that has, let's say, an I volume property is going to be routed to this actor. And this actor is going to inspect, let's say, a property on the message, such as a device ID. It's going to route all messages that belong to the same device ID to the same volume sensor actor. And that actor is going to have the ability to observe all the state changes that belong to that one sensor. And if any of those readings go beyond, let's say, the configured thresholds we have, it can fire an alert, and that can dispatch, let's say, an oil field team to go take a look at that section of the pipeline and see if maybe there's a leak, maybe there's a fire, maybe there's some other problems that might indicate that the pipeline's not operating safely. And they can go and react to that before disaster occurs. And then on the flip side here, on this side, we might have all of our temperature sensors, which again are going to have a fairly sort of, let's say, identical structure, where we're going to have our device of type B actors that are monitoring each of the different individual temperature sensors and are again applying their own specific business rules to the data that they're seeing and reacting accordingly. So this ability to run many different actors concurrently is what's going to allow us to fulfill the second guarantee. All these actors are processing their state changes in memory, and they're all able to run concurrently at very low latencies. Akka.NET can process in .NET 6, as of like the most recent version, a single Akka.NET actor system can process something like 80 million messages a second, and that's in one process. So we're able to go ahead and guarantee that each of those messages get processed with very low latencies. Usually it's on the order of microseconds in Akka.NET. So that's the second key business question answered. So we're going to take all of our state. For question one, all of our state for one given operation is going to be modeled as the internal properties and fields of a single actor type. And then in order to run many instances of that concurrently, we're going to use the actor hierarchy to spawn as many concurrent instances of those different entity types as we need. And that's going to allow us to observe that guarantee for many different instances of that operation in one process. Now we get to the third and final question, which is, how do I operationalize this in order to deal with, let's say, the failures of the network, or to deal with other issues that are more routine, such as deployments, where I have to take an instance of my process down and replace it with a new instance running updated software? How do we reason about that and build a resilient, production-worthy system? Well, Akka.NET comes with a lot of different tools and a lot of different packages that can help you address this issue. For building a fault-tolerant distributed system, it's these three packages that you typically want to take a look at: Akka.cluster, Akka.cluster sharding, and Akka.persistence. Akka.cluster allows us to build a low latency network that is designed for real-time stateful processing. And this is very different from, let's say, a normal stateless web application, in that one of the things you need in order to build a low latency stateful application is you need a property known as topology awareness. This means that every instance of your application needs to be able to talk to every other instance of your application. When you're building a web app, most web servers don't need to know about the other web servers that are participating. And that's because they're stateless. They don't really have any business interacting with other web servers. In a stateful application, you need to know which state lives where inside your system. So that way, all of the data that belongs to a single entity all ends up inside the same place in your network. And that's what Akka.cluster sharding lets us do. This gives us a tool to reason about where should each instance of my business entity be located inside my software system. And then finally, there's Akka.persistence, which gives us a simple built-in way that is database agnostic of being able to persist and recover state. This is what's going to allow us to essentially move actors from one instance of a process to another. And that's really useful for both scaling, for fault tolerance, and for being able to do things like shut down actors that aren't being used right now, and then bring them back later the next time there's a request for them, which is something Akka.cluster sharding will do for us automatically, I might add. So like I mentioned earlier, Akka.cluster is really designed to be a tool for building a distributed network of state. It uses a peer-to-peer networking methodology known as a mesh network, where every node has a direct connection to every other node on the network. That's ideal for building low latency applications. So essentially, each one of these processes here is going to host its own little hierarchy of actors. But the entities that live on node 1990 are not going to be the same as the ones that live. Actually, I guess we're differentiating by host name, not port. So the actors that live on host 3 aren't going to be the same as the ones that live on host 2. They're different instances of the same actor type. In order to make sure we have a consistent view of all of our state, we need to have exclusive partitioning of data. Akka.cluster sharding does this for you. It guarantees that we have at most one instance of each of our business entities of a given type at any time. And that allows us to make sure that we have data consistency, which is something we need in order to make sure our system functions correctly. So Akka.cluster gives us the sort of baseline for building in these topology-aware networks, which allow us to know where entities might be located inside our system. And they also allow us to know about things like changes in node availability. Like if a node is joining the network, Akka.cluster will make us aware of that, so we can start taking advantage of that new node's capacity. It also lets us know if a node is trying to leave the network, that we can migrate that state to some of the other nodes that aren't leaving. So Akka.cluster gives us the tools for being able to do this. Now, you're probably not going to interact with Akka.cluster's APIs very much directly as an Akka.NET end user. You're probably going to be interacting with Akka.cluster indirectly through tools like Akka.cluster sharding, or maybe through a tool like an Akka.cluster router, which is a really simple way of being able to distribute state from point A to point B. So clusters enable actor distribution in Akka.NET. I'm not going to have time to show my demo, unfortunately, because I think we're running up against our deadline here. But I have the demo that I do run. You can see many examples of online. But basically what actors basically enable here is that on node 1, if I create let's say a cluster pool router, I can go ahead and say, all right, I want to distribute messages that arrive here to actors that are, actually, let me rephrase that. If I'm using, let's say, a tool like Akka.cluster sharding, and I say, okay, I'm getting messages that have a property of type, I trade ID. I want to make sure that all trades end up going to the actor that owns that position. And that actor can only live on one of these 4 nodes. My router is going to be able to determine, based on who's in the network right now, and using a technique like consistent hashing, it's going to be able to figure out which one of these nodes owns that piece of data. And it'll route all the messages that belong to the same entity to the same actor instance on the network. Now, the last piece of the puzzle here to make our system production worthy is we do need to bring the database back into the picture. And that's what Akka.persistence will allow us to do. This gives us a simple event sourcing API that actors can use to persist and recover state. And this technology is database agnostic. It works roughly the same way on all platforms. So for instance, I've been doing a lot of work with the Postgres version of this. I'm working on a production application for Petabridge right now that uses Azure Table Storage. And what this does is it makes it feasible for actors to recover their state following a crash or a restart. So for instance, if I have my room message history actor here for building a chat room, it's going to receive all these chat messages from users, and it's going to use them to build up an in-memory history. Well, it's not good enough for me to just have my in-memory history. I also need to be able to make that history durable so it can be recovered again in the event that we restart the process, or in the event that this actor gets moved from one node of my cluster to another. And that can happen when we're using tools like cluster sharding, which are designed to go ahead and help maintain an even distribution of state and work for both availability and fault tolerance purposes. So when I recreate this actor, it's going to replay all the messages in the order in which they were originally saved and use them to rebuild our in-memory history. Finally, for sort of the last portion of how we make a production-ready, real-time web application, we're going to use cluster sharding. Cluster sharding is basically a way of automatically managing the life cycle of your entity actors. Every time you send a message that has, let's say, a property that you identify as a entity ID, and that's done through C# or F#. Anytime you have an entity ID that cluster sharding recognizes, it will instantiate that actor and route that message to it somewhere in the cluster. Now, if the actor already exists, the cluster sharding system will automatically route that message to the existing instance of that actor. So all messages for the same entity are guaranteed to go to the same place. And Akka.cluster sharding is able to work even across network partitions. So if, let's say, there's a disruption in the network and a bunch of your Akka.NET processes aren't able to talk to each other anymore, cluster sharding will not try to create a new instance of that actor until those old nodes that are unreachable now are removed from the cluster. And that's a process that typically takes about 20 seconds. In order for that to run. Or if those nodes come back sooner, we'll go ahead and deliver those messages back to the actor instance running on those nodes that were only temporarily unavailable. And on top of that, Cluster sharding is able to help redistribute entities as the cluster scales up and scales down. So these are sort of the building blocks of Akka.NET that you can use to build these types of real-time processing systems. The last thing I'll touch on before I get to questions is how do we actually bring this all together and expose this to clients? What's the right way to kind of operationalize Akka.NET in a cloud environment of some kind? Well, the way I'm typically building and delivering applications, whether it's ones we build in-house at Petabridge or ones we work with our customers to deliver, is usually Akka.NET runs inside a private zone. In this case, I'm using Azure Kubernetes Service. We also have customers using things like Azure App Services or container apps or ECS on Amazon. And what we have here is basically a private network of an Akka.NET applications that are all clustered together. And they typically interact directly with, let's say, a front end, either using a gRPC or an HTTP API or maybe WebSockets. And then on top of that, these actors will typically use Akka.NET persistence and a data store such as Azure Table Storage or maybe SQL Azure on here. So in terms of how we expose Akka.NET to users, we don't want to use Akka.NET Remote. Akka.NET Remote uses certificate-based authentication, which is very cumbersome to implement. I tend to prefer to use gRPC if I'm building these sort of real-time like streaming applications, such as a video game. And I'll build an HTTP API for something that's a little bit more mundane, such as a request response system, where maybe a user wants to be able to query the status of an operation that's running in the background. And then for real-time web UIs, I tend to use WebSockets. So I'm building right now, for instance, a real-time monitoring system on top of Akka.NET. That's all going to be implemented on the front end using WebSockets. And on the back end, where we do our data ingestion, we're going to be using gRPC for that. So I think I'm just about out of time. Oh, never mind. I guess, yeah, one last thing I'll mention before I get to my final slide here is how to do deployments. The one thing that is also different about stateful applications from stateless one is environment swaps are a popular way of doing deployments in stateless environments, and that only works because there's no side effects. Stateful applications do have side effects when you do deployments. So you can't do an environment swap where you go ahead and basically switch your entire environment all at once. What you need to do is do what's called a one-by-one replacement, where nodes are gradually replaced with a newer version of the software. Kubernetes does this pretty well out of the box using what's called a stateful set to do it. In Azure Container Apps, you can use a revision for doing that, or in ECS, you can use a rolling update. This is not that difficult to implement, but it's something you do want to be aware of, because otherwise you can create what's known as a split brain, where you have two different instances of the same entity with different states, which can result in business problems for you, depending on what your consistency requirements look like. You're much better off trying to do a one-by-one deployment for this. So, oops, that's all I have for our talk today. Thank you very much to the Build Stuff team for all of the great work you made to make our actual remote presentation seamless. And now I'll take a look at any of the questions that you might have in chat. So thank you.
Do we have any questions? Aaron, thank you very much for joining this early morning, as if it is in Texas. Since we don't have questions, we can just go to sleep or what? Or is
I'm just going to start my work day, probably.
Okay, so thank you very much for joining, and it was a pleasure to have you.
All right, thank you everyone who attended, and I hope you enjoy the rest of the conference.
Yay, bye.
I'm saving the coral reefs using underwater AI.
I'm helping food get to those in need, fast.